I guess while people are connecting, I can say welcome to this edition of Gauge Theory Virtual. We're happy to have Chris Herald talking to us about character varieties for tangles and holonomy perturbations. So this is good old school gauge theory. I'll let him take it away.
Great. All right. Well, it's good to see some familiar faces. It's good to see humans other than myself and my wife, and the occasional student who accidentally turns on their camera during my Zoom lectures. But it's particularly nice to see familiar faces. Hello, everybody, and I hope we get to I hope we get to see each other in person at one of those old-fashioned conference things soon. But in the meantime, I'd like to thank the organizers for the opportunity to talk in the seminar here. I want to talk about relative character varieties of tangles in three manifolds. So somehow when you have a three manifold and a knot or a link in it and you cut it into pieces, that's kind of what I mean by, relative meaning when my surface cuts it, I'm keeping track of, I'll explain that later. Anyway, so yeah, I want to talk about relative character varieties, and in particular traceless relative character varieties, and then holonomy perturbed flat moduli spaces, the sort of holonomy perturbations that are consistent with gauge theoretic invariance, although the goal here is to translate as much of this as possible into just character varieties, homomorphisms of pi1. Anyway, this is joint work with Guillaume Casassis and Paul Kirk, and then closely related to joint work with the two of them and Artem Kotelsky, which I think you heard a month or so ago from Artem about that paper. So this will be related to what Artem talked about, but focused a little more on just the structure of these character varieties. So, the setup, the motivation for looking at this is the following. Maybe everybody is familiar with this, but Kronheimer and Rovka defined a singular instanton Floer homology of a link in a three manifold. And to solve the problem of reducibles, there's this little variation on singular connections that involves putting an earring. So somewhere on your link, put a marked point, and what we do is we actually take the link and put a little linking circle around there, basically add that to the link, and then to avoid the possibility of reducible connections, if you work on an SO3 bundle, this is missing a word here. An SO3 bundle, which is non-trivial on surfaces that intersect that little arc W connecting the earring to the rest of the link. So that specifies an SO3 bundle on which there are no abelians, and that kind of solves the problem of having singularities that come into the gauge theory. And so that's the goal is to look at, well, the flat connections, the flat moduli spaces that arise in this setting. But I'm interested in, when you cut this picture into two pieces, now you've got three manifolds of boundary and tangles, and what's the corresponding flat moduli spaces of those pieces. So, so the flat singular connections that arise in this SO3 bundle can be related to SU2 connections SU2 flat connections on the complement of not only the link and the earring, but also this arc in between. So if you actually drill out that arc in between, we can work with SU2. It's a little bit easier to work with SU2 representations anyway. So my description of SU2, if I talk about specific SU2 elements, I'll think of unit quaternions. And if that's my definition of the group SU2, then traceless is kind of a funny word because quaternions don't have a trace. But of course, this is has a complex matrix interpretation. And the analog in this copy of SU2 of traceless is just the purely imaginary quaternions. So SU2 is a 3-sphere, and the set of traceless elements in here are the ones with A0, and that's a 2-sphere in the in SU2. So the well, the definition of the singular connections is that when you get close to the link, there's a holonomy around there that is actually a traceless SU2, or translates into a traceless SU2 holonomy. So, so I'm actually not going to, I'm not going to talk very much about connections at all in here. I'm going to talk about representations of pi1 using the fact that holonomy gives me a translation from flat connections to fundamental group representations. And so here's a little bit of notation. If you have let's not worry about a link for a moment. If you have a space X, homomorphisms of pi1 into SU2 up to conjugation, we'll just call that R for the representation variety. If X has a link in it, then you could look at representations of the link fundamental group, the link complement fundamental group, with the condition that all the meridians have to go to traceless elements. And I'll just denote that by, first of all, having a comma after the space for the link and a sub-zero for that trace condition. So, and if your link has had an earring added to it, so now there's an earring and there's also this arc W removed, then there's a notion of traceless on here that's relevant in the singular instanton theory, which is, well, we still want all the meridians to the link to go to traceless elements. We also want the meridian to E to go to a traceless element. And then I want the meridian for this arc W to go to -1, or in other words, a meridian of the link next to the earring anti-commutes with the meridian for E. So, so there's a slightly different condition than just insisting meridians go to the identity. These two nearby meridians for these things anti-commute with each other.
Chris, do you factor out conjugations?
Yeah, actually, all of these are supposed to be mod conjugations. Yes, thank you. Okay, so so that's the, these are what I mean by traceless character varieties. There's sort of two variations with the earring and without the earring, and then if you split the 3 manifold along a surface, then the basic question we're interested in looking at is to what extent can you capture some or all of the information in this singular instanton homology from Lagrangian floor theory for these flat moduli spaces of the pieces with the trace conditions. And note that if I split this, one part that I split it into is going to have the earring and the other part's not. So that's why there's like I care about both versions of that traceless character variety. Anyway, in earlier work with Hogenkamp, Hedden, and Kirk, we looked at some examples of splitting knot complements into two tangles with two arcs, and splitting along a two-sphere as opposed to a more general surface. And the advantage of sticking to a two-sphere to split the thing is that the traceless character variety of the surface that you get when you do this is actually two-dimensional, and the character varieties of the pieces are one-dimensional. So you can stick to combinatorial floor theory and count immersed disks rather than having to work with pseudo-homomorphic disks in your floor theory. So, you know, some earlier work looked at some examples there, and then this topic that Artem talked about some time back in the seminar is the following problem. I mean, it was inspired by the following observation in those earlier calculations. And that is, if you take the 4-5 torus knot, I'm not telling you how to do it, but there's a way to split two strands off and pick a two-sphere that encloses just a trivial two-tangle with the earring. That's what the blue two-sphere represents there. Or alternatively, you could move the earring to the other side, or make your two-sphere slightly smaller so that it's just plain got a trivial two-tangle and the earring's on the other side of the two-sphere. And in those two settings, those two different copies of a two-sphere, splitting the thing up, the traceless character variety that you get from the two pieces, these two pieces are exactly the same except for which one has the earring. And the traceless character varieties are two different pairs of one manifolds in the traceless character variety of that two-sphere with the four punctures where the link goes through it. And these two, well, the actual floor homology of these curves in the pillowcase is different. So you're not getting an invariant of the link by just picking any old two-sphere looking at Lagrangian floor theory. So that led to try to understand a little bit better, you know, what's going on in this context. And so, well, let's look back at this picture for a minute. I mean, what I described so far is two alternatives for a way to split this with one two-sphere. But of course, if you split it with two two-spheres, you have the outside of the blue, the inside of the red, and you have this intermediate two-sphere across the interval with also a pretty straightforward little tangle, just four arcs in it, and the earring happens to be on one of those arcs. And so we started studying the traceless character variety of this chunk with two boundary two-spheres. And it's singular. It's not a manifold of the correct formal dimension. You can pick some perturbation curves that run around in here and link things together. Right now, there are some surfaces that split that, allowing gluing parameters in the flat moduli space. You can find some perturbation curves that tie together those parts so that they can't be separated by a separating surface like that. And you know, that's kind of what led to this observation that Artem talked about. And just to summarize that, what we, you know, the conclusion after examining what this traceless character variety turns into and what happens if you compose with the outside three manifold on the blue side first, and then take the Lagrangian floor theory or compose with the character variety of the inside piece first, and then take Lagrangian theory. What this analysis of this example suggests is that you may be able to get a link invariant if instead of doing the Lagrangian floor theory, you use a quilted floor theory for generalized Lagrangian correspondences, including bounding cochains and related to figure-8 bubbling. So anyway, so that's the kind of, well, that's a very quick summary of what's in this paper with Paul and Guillaume and Artem. And so, well, this leads to, so for one thing, this required a good understanding of what the traceless character variety of this particular 3-manifold is, which has two spheres with a total of 8 punctures on the disjoint union of the two spheres as its boundary, where we have all the trace conditions. And anyway, this also just suggests, okay, well, maybe there's hope that you can get something more interesting. So how do these traceless character varieties work? And what I want to talk about is kind of how to understand the symplectic properties of, well, now let X be a 3-manifold with boundary, let L be a properly embedded tangle in X, and then look at the character variety of the boundary of X with the boundary of L removed with trace conditions around there. That should be a symplectic manifold, and then these 2 variations on traceless character varieties in the 3-manifold should hopefully in this scheme give you Lagrangian submanifolds in there, at least after perturbation, after some version of holonomy perturbations. So I've mentioned holonomy perturbations. I haven't said anything about what they actually are. Let me take a little bit of a moment or two to describe what's going on there. Again, I'm going to give you the translation into character varieties of what they are. The data involved in picking holonomy perturbations is 2 choices. First of all, in your 3-manifold, or in this case, in the complement of the link in the 3-manifold, the tangle, you pick a collection of disjoint solid tori, embedded solid tori. I'll call them gamma. I'm not going to differentiate between the cores or the solid tori, open or closed solid tori. And I'll call gamma the union, gamma i's the individual ones if I want to specify. And then for each of these gamma i's, pick an odd 2 pi periodic function from R to R, or or whatever function from the circle to the circle that induces. So that's the data that you specify when you create a holonomy perturbation. And then what holonomy perturbed moduli spaces mean roughly is you change your critical set of the Chern-Simons function, which is the flat moduli space, into some variation on flatness that has to do with this perturbation, well, a perturbation of the meaning of flatness that has to do with this data. And again, the translation, if you want to talk in terms of character varieties, is the resulting perturbed flat connections are actually flat off of the gamma i's, and then they just satisfy some additional, a particular relation on the boundaries of the gamma i's. So each gamma I is a solid torus, and on the solid torus or near the solid torus there's a meridian and a longitude. Longitude depends on a framing, but that's kind of part of the data in the embedding. And every SU2 element can be written in an Euler exponential form, e to the some angle times a unit imaginary quaternion. So if the longitude is e to the alpha times this imaginary unit quaternion, then the meridian for that gamma I is going to be, first of all, it's going to be commute with this, so it's e to the some other angle times the same thing, but that other angle for the meridian is related to alpha by that odd symmetry function fi. So
Chris,
you get to pick these.
Chris, just to, when you say odd, you mean like, if you think about the circle, it's just that it's odd with respect to the sort of some complex conjugation or something like that.
Yes. Yeah. Yeah. I mean, these are
Because
sort of
odd and 2 pi periodic seem contradictory. That's all. Anyway, I think I knew. I just want to make sure I understood what you meant.
yeah. Let me think about that.
It's just odd with respect to a different involution. And yeah. Anyway, that's fine.
Yeah.
Danny,
So
isn't sine both odd
the
and
bottom line is
periodic?
it's these are derivatives of even functions.
Okay, fine. Yeah. All right.
2 pi periodic.
Yeah.
That's the right thing to say. You know, except there's no point like naming the antiderivatives because this is all that matters.
Yeah.
In the effect that this has. So yeah, you're right. I think I.
No. Actually, I think actually I wasn't right, but I just was confused. But anyway, I think I understand what you mean.
Yeah. Okay. So odd symmetry says you have to take 0 to 0. Then 2 pi periodic means you send all the other multiples of 2 pi to 0.
Yeah. Okay. Thanks.
Yeah. Anyway, so the point is, if fi is 0, then the meridional holonomy is 0, and it's as if you didn't. Then it extends as a flat connection over the solid torus. But otherwise, it's a flat connection on the complement of the solid torus with a slightly different meridian condition that depends on the longitude holonomy. So anyway, that's a brief foray into talking about actual connections, but from what I've said, this means that you can interpret this in terms of character varieties by looking at pi1 of not only the complement of the link in X, but drill out all those perturbation curves. And now, you know, my sub-0 means I still have a trace condition on all the meridians of L. They go to traceless SU2 elements. The meridians of the gammas aren't required to be traceless, but they're required to be related to the longitudes for those different gamma I's by that perturbed version of extending as a flat connection over the solid torus. So that's a description of a perturbed character variety that depends on which gammas you drilled out and what are these FIs that determine the relation. And if there's an earring, then there's an analogous statement. It's just that you also send the traceless meridian to something, you know, the earring generator to something traceless. So so anyway, that's what, you know, from here on out, that's, well, let's put it this way. These are the things, the analogs of the flat moduli space, if in the gauge theory setting, you didn't have a non-degenerate flat moduli space to start with and you had to use some perturbations. Incidentally, you don't have to use disjoint solid tori in holonomy perturbations, but if you want to track the effect the way I'm talking about, then doing something like making a holonomy perturbation using a solid handle body instead of disjoint tori is a lot harder to figure out what the holonomy condition is on the complement. So the advantage of disjoint solid tori is this right here. You can just explain in terms of pi1 exactly what the effect is. All right, so the joint work with Guillaume and Paul that I want to talk about is it's really it's a result that will come as perhaps no surprise to anybody that has been working in this area for a while, but the surprise is that the proof doesn't require you to write a technical section bringing in a lot of machinery in order to justify this. So the advance here is that I don't have to use gauge theory and transversality to make a nice statement about the behavior of this, or to make this particularly useful statement about traceless character varieties. So what this, in a 3-manifold boundary with a tangle, after you've picked perturbation data, if you're at a point in the traceless character variety with or without the earring, that where the formal tangent space to the traceless moduli space has the correct dimension, and I'm putting that in quotes, but I'll spell out a little more what I mean by that. If it has the correct dimension and the restriction to the boundary gives you something in the top stratum of the character variety for the boundary, then the restriction map of the link complement for the perturbed character variety to the traceless character variety of the boundary is actually a Lagrangian immersion. So what I mean by correct dimension is that depending on what the original boundary of the 3-manifold was before you put in all these punctures and then impose the trace condition around the pairs of punctures, there's a, that has a certain dimension, and if this is half the dimension, then it's actually Lagrangian. So you get the, and I mean, if that's true at one point on the tangent space, then nearby it's a Lagrangian immersion. So all right. So I mean, let me make one comment about this. I mean, if there's no link, if this is just a 3-manifold with boundary, then and you interpret this as the actual flat moduli space and use de Rham cohomology with coefficients in a bundle, then you need to use a perturbed version of de Rham cohomology involving the Fredholm complex for the perturbed flat moduli space. And all of this can be done, but it would require you to delve into a bunch of technical gauge theory if that's going to be your proof in a paper about character varieties where you didn't really even need a definition of connections, right? So when I say we have a simpler proof, I mean, it's actually just going to be algebraic topology and character varieties. And so one thing is, let's dispense with the perturbation part right off the bat. So you can think of the perturbed character variety as you take if you drill out gamma and then look at the traceless character variety for the link in that complement, that has part of its boundary is the boundary of all these solid tori, and part of its boundary is the rest of the boundary. So that right there is a correspondence, or it has the potential to be a correspondence between this traceless character variety and just the character variety of all those perturbation solid tori boundaries. And the relations that we described, I mean, here's a little picture of the character variety of a torus. One edge here is the character variety of the solid torus in there. The meridian is just trivial, and the longitude, whatever, the longitude can be anything. So one edge here is sort of the unperturbed character variety of the solid torus and its image in the character variety of the boundary. This is the SU2 character variety. The perturbed version, that Fi just gives you some function that if you graph it instead of graphing the zero function, that's what the perturbed character variety, the perturbed, that's what the representations of pi1 of the boundary that extend as perturbed flat connections correspond to. So you could think of the character variety of the link and gamma and set of perturbation curves complement as a correspondence, and then the data I told you, depending on the FIs, just gives you a different symplectic manifold in here to compose that with, to get something, to get a Lagrangian in here. And the nice thing about this, about composing these is that if the composition comes out the right dimension, then for Lagrangians, then the pieces you started with were apparently the right dimension, and they were transverse. I mean, so if this composition comes out the right dimension, then this must have been the right dimension, and also the FIs you picked made this made this guy and the perturbed character varieties transverse to the diagonal in the in here. So the point is, I don't really need to worry about it. I don't need a different version of this for perturbations. I can just think of drilling out those perturbation curves, and now my three manifold has more boundary. And on that part of the boundary, there's no trace conditions. And then the rest of this is kind of taken care of by symplectic, by composition of the correspondences. So that leads to a simpler story. So just think of taking your link and add the perturbation curves to it. That's a new link, well, link or tangle, I should say. And some of these components have a trace condition, a traceless condition around them, and some of them don't. But if we can get a nice understanding of traceless character varieties when that in this context, then we're all set. So okay, so to simplify the notation here, since we're talking about taking your three manifold boundary, drilling out the tangle and also this other stuff, that makes a different three manifold with boundary. And all of these things are actually homomorphisms of pi1 of that higher genus boundary. Again, there could be many boundary components here. There's certainly one for every one of the gamma i's, and one for every closed component of L, and one for every, well, whatever. Anyway, no constraints on how many boundary components or whatever, but just take any old three manifold with boundary. I'll call it Z. So you can think of this Z as being X with all of this stuff drilled out. And on the boundary, there's some collection of curves on which I want to impose a traceless condition. So again, the orange here is the relating this to what we were talking about above in the more specific context. So the Z I care about is really X with the link and the perturbation curves drilled out. And C is just the meridians on the link, because those are the things where I still want to impose a trace condition. And well, no other conditions. Just forget, you can forget where this came from. Now just think about Z. It's got boundary. You pick a collection of disjoint curves. Call that C. And it turns out that just by doing algebraic topology with this surface and a tubular neighborhood of the curves and the complement of a tubular neighborhood of the curves intersecting along, you know, 2 circles for every curve in C, because that's what the tubular neighborhood looks like. We can sort of set up an argument that takes care of this Lagrangian property. So the first thing is, well, one comment which I guess I haven't made explicit, but I think is fairly well known. The tangent space to a character variety can be thought of as some H1 with Lie algebra coefficients and some flat in the flat bundle determined by the representation. So, so if I just look on this surface, H1 with coefficients in the flat bundle determined by rho, that is the tangent space to the entire character variety of the surface. No trace conditions, not treating different boundary. Well, I mean, I guess I should make one comment. What do I mean by the character variety of a surface if it's got more than one component? I mean the flat moduli space, and go think about what that means in terms of base points. So really what it means is, like, in my Z, pick a path to a base point in every component of the boundary, and then use that character variety. So that the character variety of a several different component surface is the product of the character varieties of the individual components. So anyway, so H1 with, you know, add rho coefficients or little SU2 coefficients twisted by rho is the tangent space. And so this is the completely standard classical, well, there is a symplectic pairing on here, which is, you know, goes back to Atiyah and Bott and Goldman and so on, which is really just, you take the pairing on H1 together with a standard inner product on little SU2, and that gives you a non-degenerate antisymmetric pairing. So it gives you a symplectic structure on that tangent space. And so that's in the background on the entire boundary, but our traceless character variety of the surface, when you remove the ends of the tangle, that has to do with F, where you know, character variety of F with a requirement that around every boundary component of F, the trace is 0. So F has two copies of every curve in C making up its boundary. Let's see. Well, so again, using just standard old Poincare duality and long exact sequences and so on, the subspace, the kernel of the map from H1 of S to H1 of V is, you can think of that as the tangent space to the traceless character variety of S. And that's co-isotropic And if you do symplectic linear algebra quotient on that, the smaller symplectic space you get is the part of H1 of F which goes to 0 under restriction to the boundary. So in other words, kind of traceless representations of pi1 of F, where you're imposing a trace condition around all the boundary components. And that really, I mean, that is identified with the tangent space of X minus the boundary of X minus gamma with punctures for all the tangle ends. And so, well, in this context, the traceless character variety of the three manifold with gamma and L removed, or I guess I should say, maybe I should say this is R0 of Z with the trace conditions on all these curves on the boundary. That's exactly the symplectic reduction of the entire tangent space of the character variety of Z in the tangent space of the character variety of the boundary if you, intersect with this co-isotropic space and do symplectic reduction. So, yeah, I mean, let me point out one thing that in this, let me make a comment that I guess I wanted to make earlier. When I say just take any old three manifold with its boundary and pick any collection of curves, there's a lot of wonderful symplectic geometry literature out there about character varieties and character varieties on marked surfaces with trace conditions or conjugacy classes fixed around the punctures and so on. And so among other things, there's a nice paper by Jeffrey and Weitzman that says, if your surface S was cut into a collection of curves that break it up into pairs of pans, then there's a Hamiltonian torus action for which the traceless character variety is the zero set of the moment map mod, the action of the group or whatever. This is more general than that. I'm not insisting that my C cuts this surface in any particular way. And for example, if my tangle that I started with has a closed component and you put one traceless condition around the meridian there, that's a torus with one of these trace conditions around it, and it doesn't cut the surface into pairs of pants or whatever. So it kind of sounds like, oh, maybe we have to be more careful, but we're not trying to get a torus action for which this is the symplectic reduction. I just want the tangent space. I just want to be able to do linear algebra symplectic reduction so that I know my tangent space of the traceless character variety on the three manifold is Lagrangian in the tangent space of the traceless character variety of the boundary. So anyway, so that well, so with straight up algebraic topology with local coefficients, you're able to prove the statement about tangent spaces that I made in this theorem, and so it doesn't have anything to do with how many boundary components, whether there are also boundary components that you would impose holonomy conditions on, tori on which you're going to impose a holonomy perturbed condition. This works just as well on the map in full generality. So the takeaway, let's see, yeah, so the takeaway is, let me actually remind you let me go back and show you this picture to talk about this. So in this picture, I have a 3-manifold with a link in it, and you know, with a tangle in it, I should say. And again, to solve the transversality problems, we had to pick some collection of perturbation curves that tie together different parts of that, cut through the different surfaces that allow bending parameters in the flat moduli space. So, so to start analyzing the character variety, you have certain tangle components for which the meridian is required to be traceless. You have other ones where it's not required to be traceless. And if you just describe here's the takeaway in terms of doing examples like that one that we analyzed to death. Take a 3-manifold with a tangle in it, pick whatever collection of curves you hope is going to solve your transversality problem, and pick some functions. Well, you can maybe pick some functions fi corresponding to those that you're going to use as the holonomy perturbed data on each one of those. Your pi1 can be generated by generators that are meridians. Well, let's put it this way. List out your meridians and determine which ones of them have a trace condition on them and which ones don't. For example, meridians on the gamma i's don't, meridians on the L's do. Maybe your 3-manifold, you need some other generators to generate pi1. So break up your generators into the ones that have to be traceless and the ones that aren't required to be. And then also write out the longitudes and meridians of these in terms of your generators. And write out all the relations. And then look at the set of places you could send your generators in SU2 to the however many regular generators there are, and S2 to the however many traceless ones. And you now have a differential topology problem. See what the dimension of the set of solutions of that is. Well, we care about mod conjugation, so these relations will be invariant under conjugation. And if when you impose not only the pi1 relations, but the holonomy perturbation relations on these generators, if that comes out the right dimension, and there's an issue of restricting to the boundary, am I getting something in the top stratum, whatever, that's also something you can check, then your differential topology analysis of this, together with this fact about Lagrangian, says you're good to go. You have a nice correspondence. You know, you have a nice Lagrangian submanifold. So you don't need to worry about symplectic geometry while you're figuring out whether, you know, what the traceless character variety is. And that means that, well, anyway, that's the content of that theorem. So, yeah, I guess, so anyway, I'll stop there.
Okay, worth thanking Chris. Do we have questions?
Yes, I have a question. We didn't impose any. Go ahead.
Can you say it again, Nikolai? It was lost. You say it again, Nikolai? It was lost.
Okay. No, my question was that we didn't impose any. Oh my God. There is an echo somehow.
Chris, maybe do you have, if you have two devices on, if you have two devices on, maybe you can turn one off. So that might turn.
Okay, let me try again.
There we go.
It works. So we didn't impose the condition on gamma, right? That the meridian goes to -1.
Right, right.
We didn't assume that SO3 is a non-trivial bundle on the complement or anything. No, not SO3. That we didn't assume that SO3 was non-trivial bundle.
Well, I mean, yeah. So I mean, I'm working with SU2. I'm making a statement about SU2 connections, moduli spaces here, that translates into a statement about the SO3 moduli spaces.
Yes, but there are two of them, right? There are on the complement of gamma. You may assume that the meridian is -1, or you don't assume that it's -1. And in this last statement, you didn't assume that it was -1.
The gammas, I'm not assuming, I'm not making them traceless, but rather I'm going to compose the character variety of the complement of gamma and L with the perturbed character variety for the solid tori, i.e. I'm going to impose the condition that the meridians of each of the gamma i's and the longitudes of each of the gamma i's are related by that thing involving Fi. So that's a different, I mean, I could, in terms of doing some composing, I could take the character variety of the complement of L and gamma and all the gammas, and I could require not only a traceless condition on all the L's, but on the gammas, but that's not actually the same thing as holonomy perturbing.
Okay.
Using those gammas. So it's not directly related to the...
Chris, I think what maybe Nikolai is asking is, in your last slide here, you could have also put some W arcs. You could have put some extra 1 manifold, and then your map could have had a third component which goes to +or-1.
I see what you're saying. Yeah.
Yeah, that's what he's saying.
Yeah.
You can do that, and and in fact we did, or we do, or we intend
right.
to.
If you want to put a G sub W here and it goes to the 1 manifold or the 0 manifold -1.
Okay.
Yeah, I mean, basically you can use that anti-commutativity condition in your relations, but that's not a very interesting part of differentiating the relations to see what the tangent space to the set of solutions is. But you're right, that's a detail missing from.
So I meant the capital gamma, I think, and you thought it was little gammas, but well.
Well, so in this statement here, I mean, let's say you have a link in S3, and then you connect some with the homology, with a Poincare homology sphere. Pi1 of that complement looks like meridians for your link together with generators. I mean, it's generated by meridians for your link and meridians for Pi1 of the other homology sphere you connect some with, right? So if you look at representations, some of those generators, they're not meridians of the link. They don't have to go to traceless elements. Also, if I'm going to drill this out with some gammas, those aren't required to go to traceless elements. So these G's include, if your 3 manifold wasn't S3 to begin with, Pi1's not generated by all meridians, and so you don't all have traceless elements, trace conditions on all your Pi1 generators, even without any gammas, but anyway, the point is that this is a differential topology question to which you can do some work and figure out the dimension of the set of solutions. And if it's right, you're good. You got a Lagrangian submanifold because of this algebraic topology argument.
Okay.
Other questions?
So, Chris, if I was kind of thinking about as you were going along, I was thinking about I guess it's your thesis, which certainly did use a lot of technical gauge theory say give transversality results, so now you have higher genus boundary and, so.
Right.
So could you kind of take this kind of technique using a little, sort of the additional symplectic geometry and kind of go back and sort of redo that in some fashion? Does that sort of fall out of this in some way? I mean, it's a more complicated setup because you're.
It does. I guess what's not immediately clear how to do, but you should be able to do is how do you take a three manifold with boundary? How do you show that there's a set of curves, gamma 1 up to gamma whatever, that if you drill that out also, the character variety of what's left is a Lagrangian correspondence between the character variety of the old boundary and the character variety of all these tori where you drilled it out.
I mean, it's got to be more complicated because that character variety of the surface anyway was I mean, there's sort of unavoidable singularities which you sort of dealt with stratum.
Right.
But I just wondered whether there was
this
somehow
this isn't making a statement about what's the structure around representations that are, say, abelian on the boundary but irreducible, on the three manifold or something like that. So if those exist in your character variety, you got singularities, you need to figure out what's going on. But in the nice setups of these singular, I mean, if you start with a three manifold and a link and an earring and you cut it, then the side with the earring doesn't have any, doesn't have any abelians on it. And the entire three manifold, when you don't cut it, doesn't have any abelians. So whatever abelians there are on the other side aren't going to hit the character variety of the part with the earring. So you locally there, you might get along with saying, yeah, there's some singularities, but I'm not hitting it. Just like, Casson did in a homology sphere with the trivial connection. I mean, when you take a Hagar decomposition, each of the handle bodies has singularities around the trivial connection, but the intersections of the pieces, when you put them back together, other than the trivial connection itself, are intersecting away from those singularities. So that kind of thing could help you out in this context if you're cutting a three manifold with a link in it. Does that answer your question?
Yeah, I guess I was just wondering whether, I mean, not who wants to go back and redo their thesis.
Well, yeah. So the one
but
thing
whether
about,
you could, if you wanted to,
Yeah.
go back and do it by this sort of, use this kind of technique to.
I mean, I think you could. I think you could, and it would be nice because then you could use that,
Yeah, and in the singular,
without writing
the
these
singularities are really there.
Yeah, but what's needed is I'm not giving you a prescription for picking the curves, other than I kind of said heuristically you should look for a set of curves that make sure to break whatever bending symmetry, gauge theory, gluing symmetry you have because of surfaces that split it into pieces with irreducible representations on both sides. Other than that, I haven't told you how to pick the gammas. And this doesn't tell you how to pick the gammas. This wouldn't tell you that part of what's in my thesis. You have to figure that out. But if you pick the right gammas, this would give you a way of avoiding the analysis in what the perturbed character variety is once you've shown, you got to actually say something about the character variety of that drilled out manifold that's missing the perturbation curves. And what kind of correspondence does that give you? Is it transverse to the holonomy conditions? So it is an avenue for cleaning that up considerably, but there's still something to do about making a statement that you can always pick the curves.
Thanks.
Sure.